To start this video, I have two random Christmas tree facts for you. Number one, in the year 2005, 32.8 million Christmas trees were purchased. Number two, an acre of Christmas trees provides for the daily oxygen of 18 people. Truly random facts. And that leads us into the foundation concepts. Somehow it leads us into the foundation concepts of the spanning tree protocol. You see the tie-in. Part one, there's a lot to it. Spanning tree, dropping trees around the world. We're going to talk about why that statement is true and what spanning tree does. Then we'll look at the original and start enhancing that as we go. 802.1d spanning tree and the details behind it. There is a lot to spanning tree. It is one of the huge concepts in modern switch networks. Finally, probably when we get to part two of the per VLAN spanning tree, we'll start getting into the STP port states, we'll get into the configuration, and finally, the optimization steps. Work is over. You walk out the door, it's Friday afternoon, you hop in the car and drive home, you fight the rush hour and get through the door, flop on the couch, and oh, it's good to be home for the weekend. You know that feeling. You're watching that ceiling fan kind of turn circles around, and now you think, well, now what do I do? I'm glad you asked, because now is the time for a little Friday night fun. Here's what you do on that Friday night. You grab a couple switches. Now, these are generic switches, no expensive Cisco gear needed here. Linksys, D-Link, whatever you want. Go ahead and take those switches and plug a computer into each side. It could be a laptop, could be a desktop, just one computer into each switch. Then take a crossover cable and connect the two switches like so. Now, turn off all the lights in the room. Go ahead and kick in a Pink Floyd CD or something to that effect, and grab a second crossover cable. May need a little light for this, and connect the two generic switches like so. Within seconds, you will have a dance party. The switches will start blinking like mad, lights going every which way, strangely to the tune of the Pink Floyd song. And you're sitting there going, what on earth is going on? You look at the computers and open the task manager, and you find out their processor utilization is somewhere near 100%. The reason this happened is because the two switches that you hooked up are generic switches, meaning low-end switches. They don't have spanning tree protocol installed, which means the very first broadcast packet that's sent by a computer, and it will be sent, computers do send broadcasts, will come into that switch, get sent down here, and then begin looping endlessly around the network. Loop, 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 loop. Hitting every computer every single time it loops around. Some people call this a broadcast storm. Now, I've heard it said, people go, well, what about the TTL field? I've heard that comment a lot. The time to live. Won't that packet die? Well, remember, TTL is in the layer 3 header of the packet. The only thing that decrements the TTL and makes it less is the packet going through a router. And in this picture, I'm not seeing any routers. So what you have is an immortal packet that is like the Highlander. It's running around with its little sword, chopping up all the computers on your network because the computers can't stop it, and neither can the switches. Now, let me walk through the foundations of spanning tree protocol. Switches will forward broadcast packets out all ports by design. That's the way they work. And in enterprise networks, redundant connections are good. They're necessary. You want redundancy. Okay, maybe not basic connections like 2 connections to every single switch, but I mean, you want switches to where you can have the ability to, have a switch connected to another switch and another, and some sort of redundancy like this. So if any one switch fails, you still have a redundant path around the network. So redundancy is good, but as we saw from this little scenario right here, redundancy can also be very bad. So the place of the spanning tree protocol is to drop trees on redundant links until they are needed. That's my little homonym, if you will, to help people remember what spanning tree is all about. Spanning tree will look at your switch network and say, oh, there's a redundant link. Let's go ahead and drop a tree on that line and disable it. That's really what spanning tree does. It looks more like a big cauliflower. The Only the active link will forward traffic, the single link. Now, anybody can unplug a network connection, so Spanning Tree will always be watching that primary link. And if it ever goes down, it will erect the tree off the line and allow the backup link to go active and all the traffic to forward across that one. So Spanning Tree is a good thing to allow you to have redundancy in the network, but not cause broadcast storms because broadcasts go over all of the redundant links. I have to confess, the Spanning Tree protocol is one of the most difficult concepts for me to talk about. The reason why is because what I just showed you is it. That's all there is to Spanning Tree protocol. It is designed to drop trees on the redundant links, disable them until they are needed. The reason it's so complex and the reason there's entire books written on Spanning Tree is because our networks don't look like our Friday night scenario. Our networks look like this in a smaller size network where we have all kinds of layers of switches. We have core switches in the middle tied to distribution layer switches in the major VLANs. We have access layer switches up here that connect to our end user PCs. Now, let me ask you, looking at this picture, would you say there is redundancy? Yeah, lots of it. Every single switch has a redundant uplink to every upper layer switch. The access layer has redundant links to the distribution layer. The distribution layer has redundant links to the core. Servers even have redundant links to their own switches. So if any one switch fails, we always have a backup path that can reroute around it for critical devices. But if we didn't have Spanning Tree, imagine what one broadcast would do. Within the VLAN, it would spin around nonstop, wiping out all the different devices that are connected to the network within each layer 2 domain. Now remember, the broadcast does stop at the boundary, so every single VLAN has its own little storm going on, and there's no way to stop that without Spanning Tree. So the reason Spanning Tree gets complex is because you look at this picture right here and you go, okay, redundancy is good, but now where do you drop the trees? What would be the most efficient links to block in order for us to get the best performance out of the links that we have? Now, this is where we start moving into some of the concepts behind Spanning Tree. Now, let me restate that. These are the core concepts of Spanning Tree, as in everything will build on these 4 statements right here. Number 1, original Spanning Tree, which is 802.1d, it's an industry standard, not developed by Cisco, was created to prevent loops, and I should add to that, a long time ago. This protocol has been around for a good decade, since switches have been in existence. Switches, in order to work with Spanning Tree, will send probes into the network called Bridge Protocol Data Units. You'll hear it abbreviated BPDUs that discover loops. Now, what these probes will do, let me expound on that a little, is they will search through the network and they will find all the redundant links. And all the switches will get their own probes back. It's like, picture a boomerang, right? If you could chuck a boomerang, the boomerang kind of flies through the air and flies around and flies its way back. Now imagine that concept with the switches. They've got these BPDUs, that kind of goes with boomerang, right? Boomerang protocol data units. It chucks this packet into the network. It goes kind of flipping through all the switches. You guys know what boomerangs are, right? I hope I'm talking to a boomerang fan club here. And it's going through all the switches, checking out every single link, swarming the network. It's actually a multicast packet. So that boomerang will fly through, and if there is redundancy in the network, the switch will get its own boomerang or BPDU back. And it's going to go, oh, hey, I wasn't supposed to get that back. I expected to send that boomerang out and it never returned. So there must be redundancy in the network. Now let's find out where it is. That's the goal of these BPDUs. Now these BPDUs also help elect the core switch of the network called the root bridge. Essentially, that's where all the boomerangs point to. They're all trying to find their way to the core of the network. And here's the big item to note. The root bridge of the network, or I should state it this way, Spanning Tree's election will pick the oldest switch in your network as the root bridge by default. Now you might be thinking, oh, that's good, right? The one that's been up the longest. Whoa, no. Not saying the one that's been up the longest. I mean, literally the oldest switch in your network. You know, the one that's sitting in some wiring closet that people have forgot about that was bought in 1989? You know, that's going to end up becoming the root bridge if it supports spanning tree, because the way it decides the election, I'm getting a little ahead of myself. Let's just put it this way. You don't want to leave it at the default, or your network will be optimized in the worst possible way. And I'll talk about some of the consequences when we get into some bigger pictures. So the simplistic view of STP, you can see it at the bottom. All switches will find the best way to reach the root bridge, then block all the other redundant links. Get that concept? That's the core concept. All the switches will chuck their boomerangs, and they all want to find the path that is fastest, the best possible path to reach whoever gets elected as the root bridge. Then all the other paths, the ones that aren't as fast to reach the root, will end up getting blocked, which disables all the redundancy in your network. Let's look at some examples of spanning tree protocol using the classic spanning tree diagram. Anytime you want to learn about spanning tree, you'll see this picture come up because it's one of the easiest ways to talk about it. First thing is that those boomerangs, the BPDUs, are sent once every 2 seconds out every single port. Now you might be thinking, wow, that's a lot of stuff. I mean, you think about RIP, and that's once every 30 seconds, but you're at once every 2? Well, remember what kind of ports these are. We're looking at gig links, 10 gig links, even 100 meg links. To send a little ping out once every 2 seconds, no worries. That's not going to bog down your traffic or kill the processors, because they're just little ping packets, little boomerangs, just making sure that there is no loop. And the more frequent you send them, like once every 2 seconds, the faster the switch is going to be able to determine if one of the primary links has gone down and start trying to find a backup. So here's the idea. Before we get into the two fields right here, let me just take this switch C over here in the lower right-hand corner. It's going to send a boomerang, a little BPDU, out every single active port once every 2 seconds. Now let's follow the trail of this little boomerang right here. It's going to go, it makes this noise, over to switch A. Switch A is going to get that and go, wow, I see the boomerang. I see this priority, which we'll talk about in a second, of 32.768, and I see this MAC address of all C's. So that just kind of goes into switch A's brain up here. It's going to go, okay, I see that. But it's going to pass that boomerang right along. It follows along. Switch B gets in and goes, oh, I see. There is a switch C out there that says 32.768, same thing. And it's going to forward it out all ports. Switch C gets it back. And it goes, I see me. You know, panic. Wait a sec. I'm not supposed to see me. This boomerang's supposed to go out and never come back. Immediately, switch C knows there is a loop in the network. Now, the good news is that when it sent that little boomerang out, every switch got it and every switch saw it. So it actually went through an election process while it was discovering loops. In every single BPDU packet, there are two major fields, the priority and the MAC address. Now, the priority is some value between 0 and 61,440. The default is 32,768. Can you say random on that one? That was some developer just going, let's just pick this one, and threw a dart on the dartboard. So that one right in the middle is the default value. Now, unfortunately or fortunately, you cannot set the priority to 1 or 2 or 9. It has to go in increments of 4096 because there's only 4 bits that are reserved for the priority. So using 4 bits, you definitely cannot get 61,000 values. So that's why every single one of those bit increments represents a chunk of 4096. Now, by default, we said it was 32,768. So by default, every switch ties on the priority. There's no way to break the tie. So every single switch has to rely on its MAC address. Now, I didn't say a MAC address. I said its MAC address. Because we all know switches learn MAC addresses. That's their major function. But the switch also has its own MAC address that it uses to communicate. And that will be the one that breaks the tie. And here's a big point. Lower is better. So when you're talking about switch A, C, and B over here, I just made up these MAC addresses because they're real simple. A is lower than B, B is lower than C, and C is lower than D. This is hexadecimal world over here. So the lowest MAC address wins the election. Thus, let's go back to the statement I mentioned on the previous screen. The lower the MAC address, typically the older the switch, because every single vendor got these blocks of MAC addresses that they were allocated, and when they first started producing switches, they started from the first numbers of MAC addresses, and as they produced more and more and more switches, they kept going up and up, higher and higher in MAC address, and so the newer switches will have higher MAC addresses, which you usually want the newer switch to become the root bridge. So all of that aside, let's talk a little bit about what then happens between switch A, B, and C. Remember, these three switches saw the BPDUs flying around the network, so they all know about each other. They all know that they all have the priority of 32,768, and they know that switch A up here has the lowest MAC address, A lower than B, B lower than C. So A ends up becoming the root bridge, the core of the network. The other two lost the election. So now, as its reward for being the root bridge, switch A will never ever block a port. All of its ports will be considered forwarding, or what Cisco likes to call a designated port. One port per link will be considered a forwarding port, and switch A became the root, so congratulations, switch A, all your ports will be forwarding. Now, all the other switches in the network will find the best way to get to that root bridge, the best way to get to the core of the network. They all look at their links. Now, notice right in the middle here, I have a link cost of 19. We'll talk about the cost in a moment, but 19 happens to be the cost for a fast Ethernet 100 megabit per second link. So the BPDUs traveled through all these links. They know how fast they are. So they added them up. Switch C flew around and said, well, it's 19 to reach the root bridge by going up, or I can go this way. It's 19 plus, I saw my BPDU fly across here, that's 38 to reach the root bridge. So this will be my root port. Same thing for switch B. They both designate their own root port, the best way to get to the root. Now, that's a tip for you. If you're ever doing some show commands on a switch and you see that a switch has a root port, don't be fooled. That is not a root bridge. If a switch has a root port, it can't be the root bridge because it's going out that port to reach the root bridge. I've gotten confused myself many times. I'm doing show spanning tree commands real quick and I see, oh, root port, this must be the root, but it's not. So we've now found the best way to get to the root. We can kind of assume what's going to happen here, right? You're eyeing that bottom link right now and going, that one's not looking so good, because both of them found their own little root bridge here, or the root port. So looking at this link, here's what happens. This side sees that it's redundant, and so does this side. But this side marks it as a designated port. What? You might be thinking, why? Whoa, why did that happen? I thought that was going to be blocked. A designated port is a forwarding port, but notice what I have after the comma. One per link. This is a link. Due to spanning tree standard, the way they have it, there is always one designated port per link. This side blocks. This becomes the blocking port. That's the final type. Notice I put where the tree fell. So by one side of the connection disabling its length, both sides are down. But the pain about spanning tree is if you're sitting on this switch right here doing show commands, it'll be like, oh yeah, this port right here, that one's totally fine. It's forwarding traffic. Life is good. Green light on the switch. You're going to be thinking, man, I thought I understood spanning tree. I thought that one would be blocked. Well, the truth is that it is, but only one side blocks the link. Now, as a side note, why do you think this guy did it? Why did switch C block his link and not switch B? Any guesses? That's because switch C, you probably got it, has the higher MAC address. The higher MAC addresses are not only used for electing the root bridge, or the lower ones, but also used to determine who will end up blocking the link. When it's trying to figure out the best switch to block its link, it's going to say the one that has the higher MAC address or the worst effect is going to end up blocking its connection. So I'd like to wrap things up in this spanning tree video by talking about how spanning tree finds the best path. Now you saw in that previous graphic that the spanning tree will look for the lowest cost link, and that's, you can see step 2. Step 1, figure out who the root is. Step 2, find the lowest cost path to the root. Now you can see a list of link bandwidths and STP costs over here to the right hand side. Believe it or not, that is a ratified list because the previous STP standard maxed out at 1 gig, meaning that was the end of the cost. You couldn't go any lower than a 1 gig link. So they revised it, and now you can see they're going to have to revise it again, probably when we get to maybe 1,000 gig, because the 100 gig will probably be a cost of 1. Once we reach 1,000 gig, we'll extend beyond what normal spanning tree can do. Now, you don't need to commit all these values to memory by any means, but I would keep in mind that a 100 meg link is a cost of 19, 10 meg is a cost of 100. So when it's comparing, if you have these switch ports that are uplinked, if it's looking and trying to find the best one to get to a location, and this is a 10, and maybe you got your root up here, a 10 meg link, and this is a 100 meg link, it can tell the difference. It can look and say, oh, this is 19 and this is 100. So if this is 19, a cost of 38 is by far better to get to the root going that direction than to use the 10 meg link. This one will end up getting blocked. What we didn't talk about on our little example was, what if the costs were tied? Meaning, what if we had a scenario like this underneath step 3, where the one up top got elected the root. We've got 100 meg links everywhere, so we've got cost of 19 going for every switch. And this one's looking and saying, well, I've got 2 paths where if I go to reach the root out either one, it's going to be a cost of 38. Well, in that case, it's going to use the lower bridge ID on equal cost path. The bridge ID is that combination of the priority plus the MAC address. Remember the 2 fields in that packet that I was showing you before? Priority plus the MAC address, that is known as the bridge ID. So it's going to look and say, okay, do you have the lower bridge ID or do you? And this one says, I do. You know, if that happens to have the lower MAC address or priority, it's going to say, well, then you are my preferred path to get there. This will end up being the block link. Now, if all else fails, meaning it can't find a tie between the lower port costs, you can't find a lower bridge ID, then you probably have a scenario like our Friday night party, where you have 2 switches connected with 2 crossover cables, just like so. So in that case, it's going to use the lower port. It's going to look here and say, okay, well, this is a lower port, maybe port fast Ethernet 0/1. This is 0/2. So you are the lower port. I will choose this one and end up blocking that. All right, well, that's where we'll stop climbing our spanning tree for now. To hit the high points, we talked about spanning tree dropping trees around the world, meaning it is the feature in any managed switch, any mainline upper end switch, that can block the redundant links and keep loops from happening. We looked at the original 802.1d spanning tree. It is an industry standard, not just a Cisco thing. And then I would say we can color half of this bullet right here. We understand a little bit about, oh, I colored the whole thing. Well, you get the idea. We understand a little bit about BPDUs, the boomerangs that detect the loops in the network. We understand how the elections work based on the priority and MAC address in the BPDU. And we started getting into some of the other STP details. That's where part 2 is going to pick up. So we'll end right there and then pick up with a very large example of spanning tree as we begin part 2. I hope this has been informative for you, and I'd like to thank you for viewing.